Hello everyone, my name is Carl. Welcome to my workshop and welcome to my YouTube channel. In this video we are going to be looking at the Rotax actuator, which we know doesn't work. I quite like the word Rotaxuator. I like that. I like these compound words like dyno starter, Rotaxuator, that's a good one. So we'll have a look at the Rotax actuator, or Rotaxuator if you prefer, and we're going to find out that there's a few more issues than we thought. There's certainly corrosion on the outside of it that we found in the last video, but I think there could be more corrosion problems related on the inside of it as well. So without further ado, let's get fired into it. Right, so this morning's task is to fault find the Rotax actuator, and we're going to try and get this thing going, or at the very least we shall find out why it doesn't work. So I've managed to find a circuit diagram for the Rotax actuator, and this is it on the whiteboard now, and hopefully you can see that reasonably well. So let's go through it before we start getting into the actuator itself and doing any fault finding. So the motor in the Rotax actuator is what we call a split field motor. Now, back when these things were originally built in the 40s, 50s and 60s, permanent magnet motors, small ones, weren't really a thing. So a split field motor is a very good thing for us in this application, because it means by operating or by feeding one or other of the two field coils, we can reverse the motor. So this dot here on the field coil means that it's wound in the opposite direction. So they're actually, their magnetic fields are in the opposite sense to one another. So if we run a current through this one, through the armature, it'll run, say, clockwise, and if we run a current through this one, it'll run counterclockwise. So working from the switch, we have a control switch up here which gives us shut or open. It's an SPDT switch. We're feeding it with 28 volts. The two lines from that switch come down into two other switches, which are limit switches inside the Rotax actuator. Then the current either runs through one or other of the field coils. They're then commoned up on the opposite side of each other to this brake coil, which then runs through the armature and to ground. The brake coil is what releases the brake to allow the armature to spin. So there is a mechanical brake in the back of the motor, which is permanently engaged by a spring, unless this coil is energized, and then the electromagnet pulls the brake pad away from the brake disc and allows the armature to spin. Right, so what would happen in this condition here if we went from shut to open? So if we move the switch down to this position, the current's going to flow down here through this line, through this limit switch, through the field coil, energizing it, through the brake coil, energizing it and taking off the brake, through the armature and to ground. So the motor is going to run in a certain direction to open the valve, and when it gets to that open position, so if once the motor's rotated 90 degrees through the gearbox, a cam on the end of the gearbox output shaft operates this limit switch and puts it to off, so that the current's interrupted and the motor stops. By the same token, as that cam's rotated round and moved this limit switch to open, it's come off this one and put it back to the closed position, so that the motor is now primed to go back to the shut position. So if we move the switch from open to shut, the current's going to flow down this line, through the now closed switch, through this field coil, through the brake coil, releasing the brake, and the armature is going to run in the opposite direction by virtue of the fact that we're running on this field coil. So the motor is going to run the opposite way to then shut the valve. The cam will come off this limit switch, putting it back ready to prime to be opened again, and it will then hit this limit switch and stop the motion of the motor. So that's how it works in a nutshell. Now, I've drawn here, look, a diagram showing you the pinouts of the breeze plug. So the main master pin, which is not connected to anything, you'll remember, the bigger diameter one is D. The one in the center of these three smaller ones is A, and then we've got B on the left-hand side and C on the right-hand side. And I know this from the good offices of Mr. Scott Bouchard, who sent me a lot of diagrams and documentation for the Rover APU. And one of the things he sent me was a original Rover manufacturer's notes for their training course on the engine. So it says in there that A and B gives you shut, so A and B gives you shut, and A and C gives you open. So basically B is shut, C is open. And I've annotated the drawing, you can see here, with the pin idents that we've got. So A is the common, so that's the ground, which will be connected to one side of the armature. B is the shut connection, and C is the open connection. And you can see I've written here, this point where the brake coil is commoned up to both fields is a solder joint inside the Rotax actuator, and I'll show you that in a minute. So we've got some orientation now where we are in terms of what things are connected to. So we'll now go and move to the Rotax and have a look and see if we can make sense of this. Biscuit brew. So off camera, I removed the cover, as you can see here, from the top of the Rotax actuator. There's a thread here, look, that this cover screws onto, an internal thread there, look. This cover has a circumferential groove, and when it's on there, it's locked in position and stopped from rotating by a little locking ring, which I'll now show you. So this sprung locking ring fits into the circumferential groove on this cover, and that goes into, or that little bit there, that protrusion, engages this hole in the threaded portion. So you can't rotate it by accident, or vibration can't rotate it. So what I need something to point with, here we go, we use this screwdriver. So this on top of the motor actuator is the brake pack, and you can see it's got some zinc corrosion on it, what they call zinc rust, this white stuff. Yeah, so there's evidence of corrosion inside here as well so far, not just in there in the end mounting. So if we lift this out of the way, and this was secured on by 2 long screws, which I'll show you now. I'll show you one of them anyway. So these long screws went through the brake pack all the way down through this assembly and somewhere into the body of the actuator. And they were quite tough to get out as well. I had to use plus gas on them. So again, evidence of corrosion inside the motor actuator. So the brake pack lifts up like this, and inside here you'll see we've got a couple of wires going to the electromagnet of the brake pack. We have the brake disc here, which is on the end of the motor. There's a tiny little split pin there that retains it, and I assume it's on some kind of either a key or a spline. We've got a couple of shims here that set the gap for the brake pack, and then this here is the friction element of the brake, and that's keyed to the brake pack by these 120-degree spaced lugs that then go into these tenons in the brake pack. I'll just try and get that out so I can show you it. Will it come out? Yes, it will. It should have a spring in it, but I've taken it out for safety so I don't lose it. So that's how that fits into the brake pack. This is the electromagnet portion. Here's the disc, brake disc if you like, and here's the, sorry, brake pad, and here's the brake disc. So we'll put that to one side. So thinking back to the diagram, we know that the brake pack or the brake coil is connected up to the 2 field coils, the 2 split fields, by a soldered joint, and this here is the soldered joint. So you can see that yellow sheathed wire goes into the soldered joint there. I'm just going to zoom in a bit for you. Perhaps not as much as that. Right. So this yellow sheathed wire goes into the soldered joint, and then we've got 2 wires coming out of the soldered joint, and they will be running off to the field coils somewhere down in the bowels of the thing. We also know from the diagram that connection A on the breeze plug, this thing, so that would be that one there, is connected to one side of the armature. So if I spin this round, I can show you here. I'll zoom in again so you can see it better. These are the armature connections, because you can tell that if I look inside there, I can see. Let's get some light on the subject. If you look down inside there, you'll see there's a little pigtail wire, and that's going to a brush. So that's definitely one of the armature connections. And can you see this blue sleeved wire here? That comes up, goes behind this black pillar, and is then soldered onto this tab, which is connected by a screw to this brass piece, which is connected to the armature. Now, in aircraft standard wiring convention, blue, certainly on military aircraft that I've worked on, is usually a ground. So I suspect that this is the part of the armature here that is connected to pin A, i.e. the one that's connected to the ground or the common. So we'll verify that now with some measurement. So I've got the multimeter set to ohms. I've got one side of the multimeter connected through this Wago connector to get a good reliable connection for testing, and that's on pin A of the breeze plug, which we know is the ground or the common. So we think that this blue sleeved wire here is connected to this one, that's the ground or the common, and it's connected to the one side of the armature like it says on the diagram. So if I put that onto there, 0.2 ohms, so that is definitely connected to that side of the armature. So that's we've learned something straight away. So we now know that that's A, and it's connected to the armature. So let me show you that on the drawing very quickly. I'll just pick the camera up and show you. So there you go, look. We've just identified that wire there that's connected to ground, that's A, and it's connected to one side of the armature. So now let's have a look at the other side of the armature and see if we can see the brake coil. So just while I was looking at that then, I did think that solder joint was a bit grotty, and I know I've already measured the armature, but I just want to check that. So I'll call out to you what the multimeter says. So it's 0.2 ohms, so that's okay. I'm on pin A. So the blue wire there is running through to this connector, which is then on this bar, and then this grotty looking solder joint is onto the, what you can see there, look, the pigtail from the brush. And if I go onto that pigtail, I'm getting 0.2 ohms, which is the same as I was getting from pin A to this side, to this bar. Right, so I've zoomed in, and you can see here is the brake coil. So we have this yellow sheathed wire coming down here, entering this solder joint, and then this other yellow sheathed wire, which is running behind this one, comes down here, and it goes onto this little terminal here, which is connected to this brass tab, which if we look there we can see there's a pigtail, which is a surefire sign that that's connected to the armature. So let's now do some measurement to confirm that. So as you can see, I've connected one side of the probe, of the multimeter probes, to the solder joint using a chocolate block connector. So that means that one side of the brake pack is connected to the multimeter. The other side of the brake pack is going to this connector here on the armature, as we know from the diagram. So if I put this probe onto here, we should see the resistance of the brake pack coil. So I'll just zoom out so you can see what I'm doing. Right, so you ought to be able to see the multimeter now, I hope. Maybe just zoom out a little bit more. There we go. Right, so I'll put the lead on, and we should see on the multimeter the resistance of the brake pack coil. So there you go, we've got 2.3 ohms. So that is the resistance of our brake pack coil, because we're on one side of the brake pack through the connection here, and we're on the other side of the brake pack to the armature here. So that's showing us 2.3 ohms, that's the brake pack. Now, why is that important? Let's have a look at the diagram and I'll tell you. So going back to the brake pack coil on the diagram, you can see I've written there 2.5 ohms. It was actually 2.3 ohms, but it's there or thereabouts. Now, what that tells us is the brake pack coil isn't open circuit. So one of the things that could be an issue is that if you look at the two split fields that run the motor, what's common to them to connect through the armature is the brake pack coil. So if the brake coil was open circuit, the motor wouldn't run. So we now know that the brake coil is good, and that is not what's stopping the motor from running. We also know that pin A is connected to the armature, so we don't think that that's an issue either. So what we'll do now is we'll actually measure across the armature and see if we get anything. Right, as I mentioned there on the drawing, I've just taken the connection I've undone the connection for the multimeter from this chocolate block. So we'll go across the armature, which is this connection here and this one here. So we should get something. Armatures are always a bit dodgy to measure. Sometimes you get funny readings because you're going through a set of brushes and a commutator and then onto the windings. But let's see if we get something that looks like an armature. Right. Let's see what we're going to get here. Get a good connection. So we're getting a kind of a reading that's dodging about a bit, but it's in the region of about 12 to 15 k ohms, which I would say looks like an armature. So the armature, we're going to say it's good. There's definitely something there. So we've got a path through the brake pack coil to the armature, we've got a path through the armature, and we've got a path back to ground. So that's good. So back on the drawing again, or the diagram. So we've established that everything from this solder joint through the brake coil and armature and down to ground is okay. So the next thing we need to do is look at these field coils. So at the moment, the actuator is going to either be in the open or the shut condition. It's highly unlikely that it's going to be in some intermediate position, although it's not impossible. But I would imagine that the last time the engine was shut down, it works on an automatic start sequence. So when the engine is shut down, a relay operates this switch here, and that closes the HP cock, I believe. So I would imagine that it has been left in the shut position. It doesn't really matter because it will have either been left in the open or the shut position. I mean, you would have to move this switch from the open to shut or vice versa and then suddenly lose power for it to end up in an intermediate position, which I find extremely unlikely. So what we can do, let's assume it's in the shut position. That means that the shut limit switch is going to be open, which means that we're not going to be able very easily at the moment to measure the shut field coil because we can't get access to this end of it because it's buried inside the actuator. What we can do though is on the open field coil, we can measure from this point here, which is point C, you'll remember, because C is open. So it should run through the closed limit switch because the actuator is shut, which means that it's primed to be opened. So it runs through the shut limit switch, through the field coil, to this point here, through the brake coil, through the armature, and back down to ground. So if we go onto the soldered joint where the brake coil connects to the two field coils, and we go onto pin C, we should get the resistance of this field coil, assuming that this switch is in the closed position and the contacts are good and the field coil is an open circuit. And assuming that this soldered joint is good, of course, as well, which it does look to be. So we'll do that next. The other thing I was going to mention was if it isn't in the shut position, it must be in the open position. So if we haven't got anything on this line, i.e. if this switch is open and we can't measure this, we can just go on to B because it'll be in the other position. It's got to be in one or other of those two positions. So let's do that now. So looking at the master pin here, this pin is C, this pin is A, and this pin is B. We've already measured A to the armature, so we know that's good. We're going to try and measure pin C now, hopefully through the limit switch to the field coil. So that means we're going to go onto the soldered joint and pin C. And it's important to make sure that you're on the correct pin here. I know there's only 3 of them, but you'd be surprised how easy it is to get confused and mixed up with these things. So we use the Wago connector again because it'll give us a really good reliable connection. We'll put pin C into one side of the Wago connector, and we'll put one multimeter probe into the Wago. I'll just check that we've got continuity. Yep, that's definitely connected through the Wago, 0.2 ohms. So the Wago is now connecting the multimeter to pin C, as we spoke about on the diagram. So what we need to do now is go onto the soldered joint. So that should be putting the multimeter across one of the field coils via one of the limit switches for that particular field coil. So let's go into the chocolate block now and see what we get. Right, so I'm not getting anything, so I'm going to screw that down tightly. Right, so that's showing open circuit. So that means either the limit switch is open or the field coil is open circuit. Right, so what we'll do is we'll go on to pin B and see if we get a reading on pin B. Okay, so I have moved the Wago connector onto pin B, and we're still on the solder joint, which is the junction of the two field coils and the brake coil. So what we're doing now is we're running from pin B all the way through a limit switch, which is presumably closed, to the field coil, and then out of the field coil here. So we're getting a reading of 25 megohms or thereabouts. It's kind of dodging around a bit. That's not very good. The other reading that we got through C was open circuit, so that would lead me to believe that that switch is in the open position. That limit switch on that side is in the open position because there was nothing at all. On this side, we have got 26 megohms, which leads me to believe that that switch is closed and potentially the field coil is okay, but that the switch contacts are absolutely filthy and we're getting high resistance through that limit switch, which would explain why the motor doesn't want to run, because we know we've got a path through the brake coil, through the armature to ground, but we've got a high resistance here between the pin B and between the field coil. So that needs further investigation, which means we need to go deeper inside the motor. Right, so I've redrawn the drawing to reflect what we've discovered from our measurements. So if this is to be believed, AB shut, AC open, then the actuator is in fact in the open position. So what we did was we measured from C, this point here, to this point here, the solder joint, and we found it was open circuit. So C to solder joint is open circuit. So that implies that this switch, this limit switch here, is in the open position, which means that the valve must be open, or the actuator must be in the open position, which would tell us that the shut limit switch is primed and ready to shut, so that will be closed. So we measured from pin B to this limit switch and to the solder joint to try to measure this field coil, and we got a B to solder joint, so B to solder joint, 25 mega ohms. So I think that the valve, or I keep saying the valve, the actuator is in the open position. This switch is open and it's primed and ready to shut, but I think we've got a high resistance on this switch, because if this switch was made and it was okay and this was open circuit, we'd get open circuit. So I suspect the problem is the limit switch has corrosion on it and it's giving us a high resistance path for the current to go through and run the motor, because we know everything else from here is fine. The brake coil, the armature, it's grounded. So what we need to do now is to get deeper into the body of the actuator, get to these limit switches and have a look at them. Right, so as I've just mentioned on the board, we need to get deeper into this assembly to find out where these limit switch and field coil wires go. the two field coil wires. So that yellow one, I've taken the sheathing off the solder joint. So that yellow one there, the one with the yellow sleeving on it, is the brake pack magnet, and these two are the field coils. The solder joint looks a bit ropey, but it's actually reasonable. I've checked it. So we need to get this kind of housing off, I think, to get any further into it. And to do that, what we need to do, I think, is just moving the brake pack out of the way. Well, it's not focusing, but I want to try and zoom in on this a bit. So what I think we need to do, this wants to rotate, and I'm mindful of damaging things, so I'm not going to turn it very much. I think it needs to pull up. I think to get this off, what we need to do is remove the world's smallest split pin here and take off the brake disc from the back of the armature shaft, which is what this is. And I'm assuming that's how they're going to be keyed or splined onto there. So I'll bring you back when we're in a position to start doing that. So I'm zoomed right in on the affected area, and I've decided that to take this end cap off or section off is going to be folly, because if I rotate the brake disc, you can see the commutator there going round. See it? You can see the segments of the commutator. So I think obviously this is the commutator end, as makes total sense. So I don't think we're going to gain anything by taking this off. If anything, I think that this is the motor end and this is the gearbox end where I'm pointing here now. I'll just bring you back a bit. So the limit switches are going to be at the output end, so they're more likely to be in this section. Right, so I've decided to call the video at this point because in order to get the actuator apart more or further, I've noticed that a lot of these special nuts that have got slots in them, they're actually peened. In fact, they're all peened, and you can see there it looks like someone's made a right mess of it with a small punch or a small chisel, but they've actually peened over the end of the bolt to prevent the nut from coming undone when the unit's in service. So I'll probably have to drill these out. Certainly the ones down here, I can get access. That one there, look, is also peened. You can see, look, the thread's been punched over to lock it in. So underneath here is a countersunk screw. So it's so small that I'll probably just damage it if I try to drive this out against that nut. I'm not sure how they would have done that in a bay when they would have maintained these when they were in service, but I am going to have to drill the bolt out. I think it's going to be the easiest way to not cause any damage to the rest of the unit. These are replaceable, these actuators. You can get them. There's companies like Mikel and Ray's Tech Surplus on eBay that do them for like £30, but I'd much rather try and get this one working. So it's going to be a case of drilling these out. So I think the video's long enough now, so we'll call it at this. So I just wanted to show you the other end of that screw that's got the nut on it where it's peened, and they're all like that. I think they're 6BA, and it's got a slot in it. It's a slotted screw, and so I think with it being peened and trying to drive the screw on that slot, I've got two hopes of getting that out of there, and they are Bob hope and no hope. So I'm just going to have to drill the heads off them and go with it that way. Okay, that's the end of the film, people. I think I've enunciated fairly well from my diagnostics on the actuator what the problem's going to be, and I'm firmly of the belief that it's going to be some corrosion on one of those limit switches that's causing a high resistance path through to the unit. In order to find out more about that, like I said, I'm going to have to get a little bit more invasive and drill some bolts out if I'm going to get the unit apart without damaging it. So hopefully we'll get that done in the next few days. Maybe I'll get another video out I'm due back at work on Monday, so we'll see what happens. It's possible, but you never know. Thank you very much for watching, and thank you very much for subscribing. It means a great deal to me. I always like to hear your comments and read them. Very incisive they are. Ooh, what's that going past outside? Sounds like someone's starting up a helicopter. Anyway, thank you very much for your comments. I really do enjoy reading them. And if you're not subscribed to me, please do so. It doesn't cost anything and it really helps me. And I'd love to have you along for the ride with the engine and the milling machine and all the other projects, sub-projects like actuators and things like this. So until next time, oh yeah, give me a like. I really like that as well. That's good, it helps me. So do that, please. And until next time, take care of yourselves, and I'll see you soon.